Hello again. Let's pick up again on this subject of Z-transform, and I'll talk in this video about the two-sided Z-transform. So, one of the weaknesses of this week's lecture from the MIT course, it seems he's just playing mathematical games without relating Z-transforms to real systems that respond to real inputs. For instance, what's this business about the two-sided Z-transform? How can a system have a response before the input is put in? Right. The Z-transform comes from the response function, the system functional, which is the response to an impulse. But how can you respond to an impulse before the impulse is put in? Okay. Now, a couple of reasons why this is so. We're sort of generalizing. It's not always the case that you want t equals 0 to represent the input time. Sometimes we might want to make t equals 0 to be the time that the system has its maximum response. Then the impulse response would have non-negative components for both positive and negative values of n, right? So the location of the impulse would be at negative time. So that's one possibility. Another thing is that Z-transforms are not just used for system responses, they can represent any signal. So they have applications beyond what were originally motivated by. So so think of it this way, that a Z-transform is just another way of representing some kind of signal. All right, you're basically just doing in fact, it's a Taylor series. You're doing, or well, we'll see. It's actually a generalization of Taylor series. All right, now the case where it's done in lecture when x is 0 equals 1 and y of 0 is kind of weird. So he has this signal that starts out very large and negative and becomes suppressed, and then blam, it goes down to 0. Okay. All right. So you can think of this as a signal that there was some cause in the past of the signal, and it's ringing down, and then you put in an impulse, and that shuts it off. Right. Right. So you could imagine that there's some system that you come across that's decaying. You don't know how it got started, and then you want to figure out. You kind of work your way backwards and figure out where it came from. It's kind of an unusual situation, but actually it turns out that there are times when it is useful. I don't know if you follow the physics news, but a couple of years ago, there's a big hoopla about the discovery of gravity waves. And the way gravity waves were discovered was there was a collision between two black holes that produced an enormous wave that decayed very rapidly. It produced an enormous gravity wave that decayed very rapidly, and they picked up the signal. Okay, so this is just an example of something that was caused in past time, and they see the decay, and they were able to look back and see something about the formation of the signal. Okay, so it's not too far-fetched that this scenario might sometimes be useful. Okay. All right. So in this case, he writes the y as minus 7 over 8 to the nth, u of minus 1 minus n. So what's this u of 1 minus n? What's the whole thing? This is just a fancy way of saying that y of n is 0 when n is positive or non-negative, and it's 1 when n is negative. All right, remember that u of n is the unit step function, which is 1 if n is non-negative and 0 otherwise. So u of n is just a fancy way of picking out non-negative values of n. So don't get all hot and bothered about this. Just think this is just saying y of n equals minus 7/8 to the nth for non-negative values of n. Okay. Now, if this is 1 when n is non-negative, that means that it's also 1 when minus 1 minus n is negative, right? Minus 1 minus n is negative if and only if n is non-negative. Okay, so or negative or 0. Sorry. Let's see. Yeah. In fact, this should be n less than or equals 0. Sorry. Let's see. Oh no, I'm sorry. I'm wrong. U of n includes the 0, so u minus 1 minus n is just the negative values. Okay. All right, so y of n equals minus 7/8 to the n, u of minus 1 minus n. It's just the same thing as saying y of n equals minus 7/8 over n when n is less than 0. It's just the same thing. Okay, so don't get thrown off by that. Right, so let's pick up on this idea of the two-sided z transform. There's actually two ways to expand p of z over q of z in powers of z. Or as a polynomial, I should say, as a polynomial. Okay, you could expand it in powers of z, or you could expand it in powers of 1 over z. Powers of z, in fact, is the well-known Taylor series, or Maclaurin series. I should say Taylor-Maclaurin series, because you're expanding around the point z equals 0. The powers of 1 over z, this is actually called the Laurent series. And you probably have not run across this unless you took a course in complex analysis. Complex analysis is a really key concept. We don't need to know that, but it is possible to simply expand this in powers of 1 over z like he has been doing. The first expansion will converge for small values of z, right? If z is small, then when you take powers of z, they get smaller and smaller. The second expansion converges for large values of z, right? If z is large, then 1 over z is small, so the terms 1 over z to the n are going to become smaller and smaller. Now, when you're finding z transforms, let me just say this: when computing z transforms, you always want to choose the expansion that has z equals 1 in the convergence region. And we saw why that is last time. That if z equals 1 is in the convergence region with 1 over z, that means the signal in positive time will be decaying. If the signal, if 1 over z is in the convergence region for the series for z, that means that the signal in negative time is going to be is going to converge, have a convergent response. Okay. All right. So suppose we have h of n equals 5 times 7 over 6 to the n for n is less than 3. Okay. All right. So let's see. So you get the z transform by multiplying h of n by z to the minus n and add. Okay. So we just do. So here it says n for n is less than 3. So here you can see that I'm actually taking negative values of n as well. All right. So you get the z transform by multiplying h of n by z to the minus n and add. Okay. And add the terms. Okay. So here I'm taking all these values of n. So this is n equals 2, n equals 1, n equals 0, and so on. All right. And then I group it like this. I can factor out a z to the minus 2, and then I get this nice geometric series. So it's just some algebra, right? And then once I get it down to this geometric series, I know I can collapse it like this. Okay, and this is going to converge when z is less than when the absolute value of z is less than 7 over 6. So you can see that this is a case where the convergence, where 1 is in the convergence region when you expand in powers of z. So it corresponds to a signal in backwards time. Now, in the lecture, he finds the inverse transform of this function in 3 different ways. I recommend you just break this up into partial fractions and then try the 2 expansions, expansion in z or expansion in 1 over z of each term separately, and then just choose the expansion where the terms are decaying. Right? To me, it seems to me that's a straightforward way of doing it. And sometimes one term will go one way and the other term will go the other way. And that, I think that's the case in this, for this particular one here. The term that expands in 1 over z gives you the positive response, and the term that expands in z gives you the negative response. He mentions how this z transform can be used to solve difference equations. So what did he do? Well, this y to the n minus 1 is a delay. You remember the delay was represented by r, and r is replaced with z to minus 1. Okay, so the z transform equation just replaces the yn minus 1 with z inverse times y, and then you get this expression in z. Then you expand, and then you take out the coefficients of 1 over z will give you the system, the response functional. All right, just expand it out, and you can get the unit response. Okay. Now this is a precursor of what we'll see next, the Laplace transform, which is somewhat more useful and is used to solve differential equations in very similar methods. So the time you spend looking at z-transforms is not wasted because the same idea comes back when we look at Laplace transforms. Now, the usefulness of z-transforms in solving difference equations depends on the ability to invert the z-transform. Okay? And the way you do that is by looking at standard forms. So if we go to the next page, here you have a list of signals and their z-transforms. Okay. So if you see some z-transform you know, and it's multiplied by z inverse, then you just take the inverse transform of the z-transform that you know, and then replace all the n's with n minus 1. Okay, so that's how that works. Okay, all right, hope that's helpful.